everybody, we're going to get started. Amy is stuck remotely, but she's still going to host. She organized this whole thing, and yeah, take it away, Amy. We're pressed for time.
Hey everyone, thanks for joining. Yeah, sorry I can't be there, but I'm really excited to join remotely and still be a part of this session. So just a little bit of background. I heard a lot of really great presentations from folks like Patrick on what it means to be cloud optimized, and Alexander on cloud optimized HDF5, and Luis Lopez at NSIDC. And was really just hearing a lot in the community about the fact that we could have it all. We could have these archival formats in a cloud optimized pattern. So that's where I got inspired to organize this session, where we're going to hear about how lots of different organizations are applying the principle of cloud optimization to archival formats. And I wanted to get everybody together at ESIP because I think that this is a great place where we can gain consensus as a community, and share knowledge about what it means to be cloud optimized, regardless of whether you're using a quote unquote cloud native data format. So we have can you go to the next slide? Oh, hey, Mike.
Thank you. Hi. Sorry.
Good to see you. Yeah, so we have 8 speakers. Go to the next slide. Each speaker is going to have 10 minutes. We will only take questions if we have extra time, but I encourage you to have take questions to the break. I will pipe in after 9 minutes to make sure that the speaker is wrapping up and we can move on. So you can go to the next slide. We are going to follow this session with another session after the break. So that is a working session where there will be breakout groups for any speaker who wishes to participate in hosting a breakout group. So if I'm hoping that we have a few extra minutes at the end of this session for each speaker to talk about what they want their discussion topic to be in the breakout group. And after 45 minutes in that working session, there will be an announcement for the option to switch groups. So yeah, each speaker will have like a little space in the room for participants to go join their topic, their discussion topic. Virtual attendees, including myself, will be reviewing and providing feedback on this draft optimized data product delivery guide. I'll share a link to that as well at the end, but basically if you want to also take that time, those in-person attendees, to review that, that would be great. I'd love any comments or suggestions you have. But this time is really for you and how you want to use it. So if there's a related activity you want to use this time and space for, please do so. So yeah, if there's anything like organic that comes up, please take that time as you wish. Okay, with that, let's go to the first speaker. So that's Patrick.
You know where this is over here.
So, where are you?
Okay, 2 computers. Hi, Patrick Quinn. I'm the ESDIS architect. I have a computer science background, and I'm going to attempt to give the talk that I wish someone gave me back when I was trying to figure out cloud optimized data, which turns out to be much more about computer science than science. So if you know a bit about computers and you don't know what the hell a chunk is, you're in the right place. All right, so here's my wishy-washy definition of what I mean by access optimized data. Basically, it boils down to how...
Sorry, Patrick.
Yes.
On the virtual screen, at least, we're not able to see your slides. We're just seeing the
Are we not sharing?
introductory slides.
Are you sharing the window instead of the screen?
Let's just make this.
Okay, looks good now. Thanks.
Okay. Yeah, so basically this whole thing boils down to how do I read the right bytes out of a file quickly? Those bytes happen to be science data bytes, which means these are really computer science problems, not earth science problems. They are hard problems. There's some pretty fundamental trade-offs to, there we go. There's some pretty fundamental trade-offs to how best to do this, which means that it's interesting. It's not just a solved problem yet. So why is this a new challenge in the cloud as we talk about cloud optimized data and so forth? Well, the fact of the matter is it's not. This is my kind of, I don't know, rampant speculation as to why it exists. But I think what we're really talking about here is we're peeling back the onion of optimization. Basically, things used to be really hard just to get the data files, a lot of data files in one place in the first place. And with the cloud, we have that. So we hit the next optimization problem, which is that it's kind of hard to actually pull things out of those files. And since we've hit that, it's more people are able to see the problem. More of those people are engineers. And so we have kind of an influx of engineers who understand and care about the challenges here. So let's understand and care about the challenges here. Oops. Okay, I'm going to spend the rest of my presentation really on developing a bit of an intuition about how to optimally store data. This is the example that I'm going to use. It's global sea surface temperature. Honestly, it doesn't matter. It doesn't even really matter that it's the Earth. One thing to think about here, though, is that it's like a snapshot in time. And so really this ought to be like a movie or like a big old like stack of images. This is a single file. You can imagine the entire data set is every single day for many years. Okay, inside of this file, there's just a bunch of like little stuff, basically key value pairs and flag values and so forth. And we know how to write that. Like, I think you don't have to even be particularly good with computers to know how to write out like some key value pairs in a text file or whatnot. So that's what you do to optimize it. You put it all in one place, you write it in JSON or whatever you want. You can stick it somewhere where you can read it all at once. Boom, optimized. That's most of the metadata. However, there's already, when we talk about this, there's some fragmentation in the community. Where is that one place and what is that one format? So if you say, well, this information's already in the file, so maybe like stick it at the front of the file, then that's cloud optimized HDF. If you say this information's in the file, let's pull it out and stick it in JSON or XML. Well, JSON is going to be Kerchunk, XML is going to be DMR++. If you say, let's forget this whole thing and make like an easier to read everything, then that's ZAR. Okay, so in the file, very interesting, data is the main thing that's in the file. It takes up most of the space. Huge three-dimensional arrays of data, and potentially a couple of them. It's the sea surface temperature data, and then maybe like statistics and those kinds of things. Really depends on what you're looking at. And yeah, so multiple variables. So what is the data? This was like an epiphany to me, and I'm going to feel really stupid in a second here when you all get to read it. It's an array, like literally an array. So I thought when everyone was talking about an array, they meant like some magic science array, but like it's that, like it's 16-bit integers that have a couple subscripts under them for time, latitude, and longitude. Also of note, it's big, usually. So like more than you would probably be able to fit in your system memory. So you can't really just load it into an array. And probably usually what we're talking about is too much to even want to pull down over the internet or whatnot. So you got to get a little clever. So what are some things you want to do with those arrays? Now I'm going to switch like completely different language syntax. So you might want to access and crunch on everything. You might want to look at how single locations change over time. So like fix your latitude and longitude, but look at all time. You might want to take a single time snapshot over an area, or you might want to do something fancier of like, well, like what was the Mediterranean like for the last 10 years on this day of the year? But when you look at that, one of the things to note here is that we have to serialize the data. So serialize means we're taking 3 dimensions, and serial is a series. It's 1 dimension, like a file is a 1-dimensional thing. So how do you do that? Well, the first two, you can notice they want to do the opposite things from each other. Like the most optimal thing for the first case is possibly the worst for the second. And then the last two cases hate both of them and want something completely different. So there's some trade-offs here. So the example I want to use here is, let's say I just want to like pull out the Mediterranean here, and I want to read that area quickly. Okay, I don't want to read too many bytes because reading bytes takes time to pull over the wire or decode in memory or whatever it is. So let's not overread. Nor do I want to make too many requests for bytes. That might not matter depending on where the data is sitting, but like if it's over the network, that really stinks. If it's on a spinning disk, it still kind of stinks. And so one thing that we might do is we're trying to balance out the number of times that we have to like read the file with the amount of extra data we have to read, is that we break it up into pieces, which are called chunks. So now we know what chunks means. It's just little pieces of the array, sub-arrays. You break that array into pieces, and then you pull out the pieces that you need and kind of reconstruct them. So now instead of having to read lots of extra stuff and a lot of requests, I have to make 6 or fewer requests and read less extra stuff. And I could say, well, like, why did I pick that size chunk? I can make them smaller, right? And now I'm making a trade-off of I'm reading even less extra stuff, but I'm making more requests to do it. Okay, so we have our chunked up file. Some other things to notice here. There's some places where it's nearly empty, like at sea surface temperature, there's nothing in the middle of the land. And there's places too where usually nearby data values tend to be close to each other. So like, this screams to me like you have to compress this. It compresses really, really well. But like that also just really sucks because once you compress it, you can no longer just like jump to one place in the file. Like you don't know where in the file each piece of it is because, some chunks compress better than others. So you have to somehow know where to look in the file. So you have to have some sort of lookup mechanism. So you add that and you've got your, basically your optimized data file. Now, this is another place and probably the main other place where the community is a little split on how to do this. You might say, well, these chunk lookups are in the data file, so let's move them to the front of the data file so I can find where all the offsets are very easily. That's Cloud Optimized HDF. Okay, you could do the same in JSON XML. That's DMR++ for chunk, the other way around. Or you can like make it someone else's problem, and that's Czar. Okay. And that's it. So just in summary, what you do to optimize access, you put all the small metadata stuff in a predictable place so you can read it all quickly, ideally in one read. You chunk it up. So you have to carefully pick a size and shape so that most users benefit the most. And that's really hard, and it requires real world testing against really where you're storing your data. And then you create an index of where to find all those things that you can also get at really quickly, ideally in one read. So solve problem, like, no, we have a session of why this isn't a solved problem. I'm happy to talk about like lots of stuff afterwards. There's places where I'd love to collaborate on various problems, but that can be the second session. That's it.
All right, we're going to hold questions till the end. Right, Amy?
Yes, we're going to go to Ryan next. We're going to hold questions till the end, yes.
Do you know how to put... There you go. And then do the slide. This is full screen, maybe. No, I think we're gonna go. This is down here, right? Here? No. How do we go to? Yeah, that's all right.
No, not at all.
Where's the?
Nope.
Yeah, where'd it go?
If people are fine with that, it's bad.
I need to go back to. It's going back to the. This much.
Nope, sorry, I got nothing
Just
for you.
get. Just gonna go
Scroll through.
Yeah, just go through this. All right.
All right, starting my timer. So thanks for having me, Amy. Sorry you couldn't make it. Today I'll be talking about maybe a companion or a good follow-on to Patrick's talk. So I think the order was good. Supporting ARCO ethics, and this will be about NOAA operations. First, I just want to put a PSA out there for everybody. Be tick aware. I found out last week I have Lyme disease, and it's been kind of crushing me. But they're there. Lyme disease is here. So if you're hiking, please be aware. So jumping in, I'm really into definitions and requirements. So I'm going to go back to this what I found as kind of the seminal paper on ARCO definition. And you know, some of the audience in here actually probably were the authors of this. Analysis ready jumped out at me. Any data set that's been pre-processed that fills quality standards required by the analysis which will be performed on it. And to me, this says it's contextual, right? Cloud optimized data formats support direct access to data subsets without computational overhead. So kind of what Patrick was talking about, pointers and headers and things to not move the data as much as possible. And again, there's lots of nuances, caveats, options, and considerations, right? As Patrick said, this isn't a solved problem. I put this graphic up here, and thanks also, you know, to Patrick for authoring this paper. This has been really important to our work. This study came out in 2020. Chris Linus and Patrick, I think, were the primary authors here. And you can see there's a lot of you know, analysis that goes on which format for which type of data. I think while some of the details have changed and we've seen some new tools, the complexities in the choice persists. Moving into ethics, you know, that's a theme of this this conference this year. So, you know, what is data ethics? You know, and I found some good definitions, and we've been talking about CARE for a while now. But I think data ethics aims to ensure that data is used fairly in a non-discriminatory way. And of course, this is contextual. It always depends, right? It's relative. You know, CARE ethics focuses on characteristics of data that will facilitate increased data sharing among entities while ignoring power differentials, historical context, right? That keyword context. You know, there are different users of our data, and that gets to my point here. And this is my opinion, but you know, ethics around ARCO might be thought of as dealing with strategies around management, and this is from a government perspective, but around limited enterprise government resources. We have very limited resources in the government to determine what formats we should prefer and how to communicate analytical readiness, maximizing fair value to the entire stakeholder body, which is essentially the entire taxpayer base, and then partners, right? And so it's very broad, right? Limited resources, lots of stakeholders. We want to support everybody as much as possible. How do we do that? How do we produce the right formats, and while still respecting these principles of care and trust and those other parts of ethics? You know, and I would argue that this must be objectively and empirically demonstrable in an open and transparent way, and that means, you know, for audit purposes, so I can say yes, this decision was made with, you know, for these reasons, and then for automation. And that second point gets into this concept that I've been working on for a couple of years in the Geoverse, right? And one of the things about the Geoverse is it defines sort of what's going to happen in communications architecture in the Web 3.0 world. And at NOAA, we've been working on an operational archive for the cloud. And this is backed by a knowledge graph and a special type of knowledge graph, which is sort of a knowledge graph ecosystem called a knowledge mesh. And this has become very important to NOAA on the whole. And last month or 2 months ago, we released a broad agency announcement and have had enormous participation and interest in helping us define, how to operationalize this. And specifically, we call out this is to expand use, reproducibility, trust in our systems to inform decision making. And this is very strongly tied to digital twins. And that's what I kind of want to get into next is this idea of a digital twins foundation. Because digital twins is a new communications architecture. It's a new communications paradigm. And we've been working very closely with NASA AIST on developing standards here and working on various pilots. And we have lots of partnerships with NSF and CNES and Ditto and Destiny to sort of found what is this communications architecture. And really, the core of this is interoperability and layers of interoperability. And we need to address all these, or we do address all these in sort of a structured way, right? And these are all fundamentally model-based, right? So we have requirements to define our open science architecture. We move through for syntactics to schematics, right? Key-to-key matching, interoperable tasks, to interoperable models, ability to share, functional requirements like real-time processing, decision capture, and essentially we've created now and defined collectively this communications architecture, which we're building things on top of. So what the knowledge mesh provides in terms of ARCO and that ethics that we're talking about is this semantic observability and this full provenance. It insists on full provenance. And this idea of observability frameworks has become very important in the past few years. And I've been presenting on this even at ESIP since the mid 2010s. But it's really become very critical into this new communications model, where we see the ability to decompose things in simple terms and then make them near to users, making them easy, sort of the rich Hickey model of thinking. And you can see here the architecture is very simple. We have storage that's linked to user business logic, so anything can sort of run here, but we're insisting on that capture. And every time we run these processes, we're capturing things, and we're doing this in semantically, interoperable ways. So how does this relate to operations? Well, the new archive at NOAA is based on this sort of framework and architecture, and we have, of course, a ConOps, which shows there are roles in this sort of paradigm for everybody, right? So, contributors of user business logic, scientists, developers, operators, metadata managers, the ability to, feed catalogs of all sorts, and the fundamental ability to show all this provenance and make it semantically interoperable, right? So easy to use, easy to start using, and then easy and accessible to access tools, right? So a little bit more on the architecture and sort of linking to more specifically to ARCO. Here you can see sort of using this core OAIS reference model, we have this concept of identity units that pass through different context spaces. And all these are information models that couple both the definition of the model and the user business logic. And those things are loosely coupled in the sense that we can reuse these things and recompose them and essentially eventually do dynamic process composition, but also do deep probing and root cause analysis of things. And we can make them so we can automate access rights and maintain data sovereignty and resource sovereignty. We'll just look at this slide briefly that shows this observation framework. Thanks, Amy. Is really capturing sort of this full picture. If I was a little bit more cynical, I would say this is a full surveillance architecture. But really, this is kind of critical, especially as we get into AI safety and exploring some of the tools that we're looking at now. And you can see sort of in the process model, it's really easy to sort of describe things, and things become self-describing. So I can say, here's how I harvested minimal viable metadata. Here's the storage. And I can swap these things out as formats evolve and my entire sort of enterprise comes on board and we see this works better for this use case, for this user, and this user's maybe more important for these reasons, we can evolve, and then we capture provenance. And we're exploring all sorts of different analytical pipelines for that. So that's my ringer. This is,
time's up.
yeah,
Thanks.
yeah, thanks.
So next we have Douglas and Harsha. Harsha.
There. Let's try this.
Hi, Amy. Can you hear me?
Hey.
Yeah, so my internet is a little unstable, so Riley will present on my behalf. My apologies
Okay.
for that.
Okay, great.
Sorry.
Thanks,
All right,
Harsha.
thanks Harsha and Riley. Thanks everybody for including us in today's session. And we're going to be providing the perspective of, how do we support cloud optimized access from a high performance computing center. So we're a smaller organization, the National Center for Atmospheric Research. So we're on a bit of a different scale from these large institutions and agencies that are talking here. So I'll just provide a brief overview of our use case, introduce what it is and what we're trying to do with what we're calling cloud optimized formats, so our user communities, access patterns, and then some brief testing results. So in terms of our user access patterns, as a high performance computing center, really our goal for data proximate compute is to support those users that are actually running their workflows on that computer system locally. So in terms of the scale of the number of users, that's typically in the thousands. And they have access to high performance compute resources as well as data analysis and visualization capabilities. And they have direct access to disk via POSIX systems, and those systems are in the hundreds of terabytes range for storage. So typically that user community is happy with what they have and they get what they need out of that setup. But then we have our external users that have access to that, what we call data commons resource as well, and they're all remote. So historically, they've gone with the download and analyze workflow to their laptops. And then what we're describing here are model outputs and in situ observations, and we're more on the PI researcher generated type of data set, as well as some institutionally produced data sets. So, we're dealing with output from weather research forecasting model in their native NetCDF, which is not CF compliant or anything. So you're dealing with a lot of weird metadata, a lot of structures, and the researchers don't really want to clean that up. They just want to hand it to you and you take care of it. So now we're working with a broader national cyberscale initiative at NSF that has kind of pushed us into looking at what I call streaming access, which is a more scalable variety of things provided by OpenDAP in the past. We're currently provided by OpenDAP, but we want users to be able to stream data into whatever compute platform they're working on without having to download full files using some of the paradigms that are being described today. So in terms of the bigger picture, the cyber infrastructure, national scale, international scale cyber infrastructure that we're working with NSF on, it's called the Open Science Data Federation. And what this is a network of what are called origins and caches. So at the National Center for Atmospheric Research, we host what's called an origin server. So if a user comes in, let's say from Germany, and they want to download a byte or a chunk from our origin server that has a certain namespace, they'll hit that namespace, and then it'll hop over to the cache that's closest to them on the high performance backbone that's available, and then they'll get that from that cache. And in the future, when somebody comes along, let's say they're in Germany, they'd get their data from the cache that's in Austria in the future if somebody else has already downloaded it. So that's kind of how that works. It's a spoke and hub system. And what we're working on and what Riley will talk about is our support of ARCO streaming access through this ecosystem. And kind of what we're going for and what I think this is going for is a compute agnostic storage platform. So whether I'm on the commercial cloud, my laptop, a university cluster, the idea is that you can performantly access data from the storage layer wherever you're at. On this figure, just kind of briefly, is a real rough schematic of what maybe a global data mesh looks like to support this logic. So with that, Riley, you can go ahead and take it away. And we've done some basic testing of POSIX versus HTTPS, and I don't think there's anything that is going to be a big surprise here, but we want to just confirm, what our assumptions are. So,
Yep.
Riley, are you on?
I'm on. Hopefully you can hear me. So yeah, basically we're just doing we want to make sure that we're going in the right direction with our transition to more ARCA ready formats. So here's just a basic example. As you can see, this is each file is about 1 gigabyte in size. We have about 24 chunks per file, and really what we care about here is just being able to read fast, right? What you could do already is you could download the file, and that's going to be relatively fast. But what we want to get out of this is this cloud optimized portion of it, which means parallel reads. So one, we care about reading locally, and two, we care about reading over HTTPS. So this is being tested on NCAR's cluster, Casper. So I'll go to the next slide just to see some graphs of what we found. So as you can see, POSIX access is actually pretty similar. NetCDF maybe leads slightly. And we're going to leave it that way anyway. We're going to have NetCDF files in perpetuity as far as we know, because the PIs are still giving us the NetCDF files, and we can't transition entirely to something else, right? We can't go entirely to Zarch. It's going to be too much. But as you can see here, with HTTPS access and NetCDF, C libraries just aren't really up to the task of reading in parallel. So you can read these files, read the individual files in parallel over HTTP, but once you get into the actual reading of the chunks, it gets more and more difficult. So we'll keep going here. Obviously, the POSIX similar performance, HTTPS, ARCA formats perform better. So I'll briefly mention here that I'm pretty bullish on ARCA formats, not necessarily because they're cloud optimized, but more because of the analysis ready part. Using Zara or Chunk, we're able to represent these files in virtual aggregations. And I think that's kind of the real power of these formats, where we can represent something like, thousands and thousands of files as maybe one reference. So that's what I think we're going to be moving more towards. However, there are some challenges with that. So I'll go to the next slide. And the biggest one we have right now is that if we are trying to automate the transition of changing a bunch of NetCDF files, GRIB files into this, chunk format or reference file, if there is some sort of inconsistent chunking across the data set, we just simply can't do that right now. Now, sidecar files, like a one-to-one match between the NetCDF file or the GRIB file and some reference file, is still helpful for accessing over HTTPS. It's still not really what we want. We don't really get that analysis ready component of ARCA. So another thing I'd like to talk about is the OSDF software stack is still developing. So being able to do these caches across the world is still a work in progress. And the last point is the catalog solutions. Right now we're using intake, but there doesn't seem to be any real standard for how our catalog files should be labeled and how people should be using them. Is Stack the answer? I don't know. I think we would like maybe more of a community consensus on how we're actually searching and discovering the data once they've been produced. I think next slide, it might be it. Okay, that's it. Thanks.
Thanks, Riley.
Awesome. And yeah, Rich, you're up next, so
Yeah.
go ahead.
Yeah. Thank you. Okay, Shift. I think the magic thing is Shift F5. And then how do we get rid of that thing again? Okay, here. Thank you. Okay, I'm going to talk about a strategy for publishing big data at USGS. This is work. Amelia, can you raise your hand over there? Amelia Snyder over there. And I worked on this together. Some kind of strategy for publishing big data that's affordable and performant. Okay, so one second. Sorry, I realized it's there. Okay. Okay, so we knew that we wanted our data to be accessible in this kind of pan-geo pattern where we're working with Xarray, we're using Dask, we're accessing data, as you just heard, from lots of chunks in parallel. We knew we wanted that. And we knew that in order to do that effectively, our data has to be out there for the users in this 100 gig network. We need it in the fast network. USGS itself is in a 1 gig network. And we have one place, Eros, it's 10. But we want our data out here, in the commercial cloud. If we were at DOE, would be okay. But we need our data over here, and we expect that our users are probably going to be doing their big crunching here, right? As we just heard, you want to be data proximate with your compute. So when you look at the cost of cloud storage, so we had one data set that was a petabyte. If you wanted to store a petabyte, at least at the commercial rates with, on demand at the commercial cloud providers, it's around 200K per year for petabyte. Of course, you can work some deals probably, but these are published rates anyway. Cloudflare, and those all have egress fees, right? So we want an egress fee-free solution because we're trying for like open science, right? So obviously, we'd like to be on an open data program that over there on the right, which is free. And then if we can't do that, we would like to be on something cheap. And the cheapest thing right now is the Open Storage Network, which is hardware you buy for 100K. You get a petabyte, you park it at a HPC center somewhere, and you're on the high-speed internet with your object storage. Okay, so this is what we actually just figured out. When we started this, we have something called Sciencebase, where everybody publishes their data at USGS, and they had a 5 gig upload limit. Okay, so that's not going to work. So we eventually landed on the solution of if we publish our data, the official USGS publication has to be on a trusted digital repository, and that has to be on a USGS computing system. So we chose to put it on a tape robot. So we take the original NetCDF files, we have done nothing to them coming out of these big models, and we put them on a tape robot with a Globus endpoint. So you can get to the data. That's the official government trusted authoritative source. But we don't really expect that our users are going to go there, right? So we're going to create a high value data set instead, where we might rechunk the data as shown in the middle here. We might reduce the information content if we want to save costs by using something like XBit Info. And then we want to see if like one of the Planetary Computer or Open Data is going to take our data set if they are interested. And if they're not, we're going to put it on the Open Storage Network working through a third party, because the third party now, since the data has been published, can take our data and publish it in a form that's performed on the high-speed internet, which we can't do directly as USGS, right? But we can help them. We can actually even fund them, right? There's no problem with that. So our first test of this was a 15 terabyte data set. It was a coast forecast model, and this is the publication page, and there's a little link to a Globus endpoint there that you can barely see, and that's good because who wants to go to Globus and start downloading these 2 gigabyte files off of the tape drive? But you can't. And if something goes belly up, we could recover and get our data off of tape. We would much rather have our users go to, in this case, Amazon Open Data accepted our data set. Yay! So it's managed by Fathom Science. Nobody in this room has heard of. They're just a tiny consulting company who we worked with, and they made the application to Amazon. Amazon said, yes, that looks like a valuable data set, and we could work with them to get the data up there. In this case, so this is just an example notebook that's up there on the Open Data page, and we open the data set with an intake URL. We do this for a couple of reasons. One is that if the data moves off of the, if the data itself moves off of the open storage, the AWS Open Data, we can just change the catalog, and the user can still run this notebook. Well, at least maybe we'd have to move the catalog actually. So you open it up, and just like we saw in the previous talk, we've actually rechunked this data set into 168 in the time dimension. We're just looking there on the bottom at that little figure. And this is to facilitate time series access. Like rechunking is often the missing step, right, in a data provider. We can't do this with all our archive data sets, but if we're producing a new one, we should rechunk usually. So this is just showing that, you can access this without a cluster. You can grab a map, as we just heard about the different use cases from Patrick in the beginning. You can grab a map in 5 seconds. You don't need a cluster. It's only 8 chunks of data. And if you want to pull a time series from the entire thing, you can spin up a cluster. I really like using coiled. This is, you know, you can pick your instance types and which region you want to run in, so you can be close to the data. And I'm going to talk about that in an unconference thing tomorrow, if you want to see how that works. And you can pull the entire time series in 21 seconds with that little cluster of 60 workers. And then going to the coiled dashboard, you can see how much that cost. There's nice accounting, and it costs 2 cents. So we had another, so then for the second thing that we published this way, this is the petabyte size data set that exists on tape as the official source here again. But if you scroll down on this publication page, you get to a link that takes you to this documentation about the intake catalog. And in this case, we actually process the data into ZAR. Actually, I again neglected to say that on the first data set, we rechunked the original netcdf files into 1 week ZAR data sets in parallel. Okay, so we were running on HPC. We produced all these 1 week ZAR data sets, and then in parallel, we converted each ZAR data set back to netcdf. And that's what we published on the Open Data Program with the Kerchunk information and the intake catalog, right? So best of both worlds in a way, right? MATLAB people or whatever can still get their netcdf file if they want to, and you know, and then everybody who's using Python can benefit from ZAR-like performance. This one we did as pure ZAR, and I'll just leave that slide up there and move maybe to the next speaker.
Great, so next is Alexander.
All right, let's see here. No, actually, we're going to go with Andy, actually. So.
Oh, right, sorry, Andy.
No, we're switching it around. So, this one, right? All right, shift F5. And then more flip. Okay.
Great. Well, thank you. Yeah, as I'm not Alexander, we decided to switch because our talks are related and it's better for me to go first than Alexander to correct and fill in anything that I missed out. So I'm actually, I should say, I'm presenting this here for Luis Lopez, who's done the bulk of the work on this and has been driving this, along with help from Alexander and Jeff Lee, who produces the ISAT2 data at NASA. Amy Steiker is also helping us on this project. Sorry, click the slide. Oh. And now we will work.
Yeah, just click here, I think, right?
Yep.
Yeah.
Oh, okay.
Sorry.
And yeah, we're not doing this alone. We actually started this project off at ISAT2 Hack Week, which a few people in the room. Amy was part of this, so this was effort with a lot of people involved. So just like to recognize those people. Okay, so if you're not familiar with ISAT2, NSIDC, I'm from the National Snow and Ice Data Center, NSIDC. We host the ISAT2 data at the moment. It's the first product that NSIDC have migrated to the cloud, and we've realized that we need to provide a performant way to access that. ISAT2 is a photon counting LiDAR. It's a laser altimeter, so it's measuring the surface height of the Earth. It measures using 6 beams, measures photon heights every 70 centimeters. So you can imagine these are big files. There's 1,003 variables in the basic science data set that we're working with, and it's stored in HDF5. You can see here at the bottom, there's a little histogram of file sizes, which range from anything of a 1 gig up to 10 gig. So we're dealing with some reasonably big files, and we need to be able to access them performantly. And we need to find a way to optimize HDF5 in the cloud. So just going back to some things that Patrick was saying, why is accessing HDF5 in the cloud slow? Most of you know this, but this little sketch kind of shows that metadata within the ISAT2 HDF5 files is scattered throughout the files. So you have to, and it's in 4 kilobyte chunks. So you have to do a lot of reads to get just the metadata about the data to be able to access it. And then you've got to access the data itself. So a lot of reads, a lot of time, not very performant. So the approach we take is working with Jeff Lee at NASA is to move all of these orange squares, the metadata, to the front of the file so that we can read them in one go. And then we also do some rechunking in some of the tests that we run. So this is kind of the file structure and the access pattern that we're using. You've got at the top here the cloud optimized format where we've moved the metadata to the front of the file in a 8 meg chunk or page, and then the bottom here you've got the original file with metadata distributed throughout it. We're using a tool that Luis developed, Earth Access, which uses FSPec under the hood to create a virtual file system in order to read the HDF files from cloud storage into a POSIX-like file system, and then we're using HFPy as the way to read the HDF5 files. And we stopped there in some of our tests, but a lot of the community using Xarray to work with ISAT2 files. So so we also are running some tests using Xarray, which ends up doing a lot more work in getting coordinate variables and attributes. So it's doing way more than just reading a single array of photon heights, which is what's happening when we're just using the HF5Py or H5Py data. Now, in order to make this really work, we can't just restructure the files. And this is something that Alexander will fill in later on. We have to set some parameters for both FSPec and H5Py in order to be able to read a large enough chunk of data without reading too much data. And this is where we're setting cache type and the block size that we read here as an 8 megabyte block size. So we're matching that block size to the cloud optimized block in the data. And then we're also changing the page buffer size in HF5Py to be equal to or larger than that. So we're not, we can minimize the number of reads. And here are the results. It's a little busy. We've been playing around with both just modifying the metadata, that is moving it to the front of the file, modifying the metadata and doing some rechunking. We're also experimenting with 4 meg chunk sizes and 8 meg chunk sizes, and then using HF5Py and Xarray as the tools to access those data. But we're also interested in other tools. H5Coro is something developed by JP Swinsky as part of the Slide Rule project, which is actually a cloud optimized HDF5 reader, different from H5Py. And we've also looked at using Kachunk as well to read that data. And you can see that by moving the metadata and by rechunking, we are getting better performance. Although in some cases it's only slightly better, and we're still kind of working through some of those issues. But when you look at the Xarray reads, which a lot of our community are using, we get significant improvements in performance from just reading the original files. And you can see the difference here between where I've marked that we're configuring the I/O and not configuring the I/O. So if you look at the 7 gigabyte file read there, then there's a considerable improvement between those two approaches. Kachunk is still a lot faster, but that involves creating sidecar files for all of the ATL03 files. So you've got to do more work processing that data in order to generate those. H5 Coro, we're still kind of working through some of those issues. Perhaps I shouldn't have included it, but I just wanted to kind of keep consistent with some of the other plots like this that you would have seen from Louis. So in summary, accessing the HDF5 files in the cloud is slow. Because of the metadata being scattered throughout the file, we can speed up access without having to do a great deal to the files. We don't have to get it out of this archival format by aggregating metadata and by rechunking. But in order to reap those benefits, we have to configure the I/O to match the page file size and the chunk sizes. And with that, I'll finish, and hopefully Alexander can explain some of that in more detail to you.
That's for Andy. You haven't heard me yet, so it's premature.
We're good? Is that yours?
Yeah.
Okay. Good. All right, try this one.
And so if that doesn't work, try these 3 dots.
Oh, wait, no,
Get
it did
that
work. It did work. It did work.
Try 3 dots here. Percent.
Okay. And then
I'm floating. Yep.
All right, so I'll sort of explain some things that Andy didn't have to explain, and hopefully clarify some things and decisions. Oh, it's down. Click on the slide. Oh, yeah, right. So glossary, but I'm sure the people here know all these acronyms. Anyway, so cloud documents HDF5 files. Obviously, this applies to NetCDF4 as well, because we are talking about the bytes in the file, not anything else. So this is not some kind of a new file format or some kind of convention on top of HDF5 file. It's really just rearrangement of all the bytes structures that are in an HDF5 file to sort of provide this better cloud performance. So these files are as normal plain vanilla HDF5 files as anything else. Andy explained about this internal file metadata approach and the larger chunks, so I don't have to talk about it. Interestingly enough, I actually talked last ECIP summer meeting a lot about these methods. So there is the QR code to the YouTube video that ECIP provided, so you can look at and see all the other possibilities how one can optimize HDF5 files, but I didn't want to talk about too much about this. So largest chunk sizes. I always try to define. I'm talking. You have to be clear: chunk size or chunk shape. In chunk size, we're talking about bytes. It's a different thing than chunk shape, and so that's something to always differentiate when you're talking to someone or someone is explaining two things. When I say chunk size, and what we are talking about chunk size is that's prior to any filtering. In other words, that's the chunk size that exists in memory before being written out. So it's not compressed or anything else. We've done some testing, obviously, with ISET2, and there's some also work with NiSAR, but I don't think we had enough cases, obviously, to be able to say what we've seen so many other use cases to be sure what we are recommending. But generally speaking, the largest chunks always are better for cloud access, and everyone talked about that as well. Because one of the things, why? Because larger chunks, less of them, it means you have to make less requests for the same amount of data, and then obviously because there are less of chunks, there is less information about them in an HDF5 file, so internal metadata is less. So consolidating internal metadata, again, I talked about 3 methods. Only one was really currently being evaluated by ISET2 and NiSAR, and this is the one that's, there's a long title. It's Paged Aggregation File Space Management Strategy. I call it paged file. Basically, the file is divided in pages of a set size in bytes. And the library, when it writes that file, there is a clear difference between pages that hold internal metadata and pages that hold the data. And if you're good at estimating your page size, you can get lucky and well, not lucky you know what you're doing, but basically you can get all your internal metadata in one page, which means that then that page is read once and no more to find everything what's in the file, plus the attributes and everything else. So for the chunks, and I'm talking about the single file, so I'm not talking the approach that some other people are talking about when they already have a bunch of files and then they're rechunking them after the fact. This is more the sort of the operational production environment. We are churning out those files as they're being processed operationally. Obviously, the size has to account for compression or decompression when people are reading those chunks, and these chunks have to be read and processed separately. By far, the NASA used this data using this zlib compression method, which is used typically because it's the most widely available. So you don't worry about interoperability. But I'm not sure that this method is any more applicable to any kind of data anymore. I think we should be more sophisticated than that. One of the reasons why is because if you have these chunks compressed better, therefore they're smaller, once they get written out, more of them can fit into a single page. And there is a benefit for that. So anyway, this chunk size, I don't want to get into this discussion, so don't worry about it. We want to finish this session on time. For these paged files, so again, I personally and ISA2 and ICER in different ways looked at different file pages between 4, 8, and 16 MB sizes. In all tests that I'm aware of, 8 MB page provided slightly better, not tremendously more, but noticeably better performance than the other file pages. Again, why? Because you're reading per page these files and accessing data per page, and apparently AWS S3 kind of likes 8-ish MB in terms of sort of the between the latency of the request and how much data comes for one request. However, when you produce these page files, they do increase the size of a file compared to the original file. So that's a little, I won't say shock, but it's like, oh wow, now we have to pay more for storage, which only works if you have the original files. NiCER will not have that problem because they'll have cloud optimized files from the get-go. So, but with ISA2, it seems to be that they thought anything less than 5% overall increase in total file size is acceptable. And with ATL03, I think we are, what's like the last result I've seen, and I think it was like less than 1%, something like that, with cloud optimized files. Again, depending on the file content, some of these pages with internal metadata will be fuller, and some of them are not going to be full with data, but don't worry about that. You want the benefit of everything in single page. That's the price to pay for that consolidation. Everything else that we discovered here, especially this bolded thing, is again from ISA2 specific processing, that if you really are creating the final file from a couple of open and closed sessions, then there are some techniques in the library that you have to enable, otherwise the file will balloon in size. And again, that's, I think, only unique, well, not unique, but only with ISA2 I learned about that. But other than that, if you write out file once, you don't have to worry about it. H5RePack, which is a command line tool that comes with the library, can basically defragment the file and produce a much smaller version if that happens. I don't know how much doing by time, but anyway, what I'm talking about this, and this is important, really applies to the version of the library 1.14.4. So if you're using anything that you are not on this bandwagon. So yeah, upgrade if you want to get any of this. Andy talked about this FSPEC and H5Py. That's sort of a privilege of Python users. The native way the HDF5 library access the S3 is this read-only S3 driver that you have to actually build when you're building the library. Doesn't come always. Conda Forge HDF5 package has it. H5Py version of the library from PyPy doesn't have it, so you have to be careful there. This read-only driver has a little bit benefit because it's kind of sort of integrated with the library, so they communicate better. What Andy was saying with FSPec, you kind of have to configure FSPec so to work with the library correctly, which you'll have to do with this driver. These are the sort of the improvements we did over time. It's work in progress. By far, HDF5 library is still not cloud optimized to the maximum possibility, but we're making some progress. Some of these settings that Andy was saying that we have to do in this latest version, the library comes with it, so it's not going to require you to do it, and that work will continue. We're trying to do as simple as possible for people to basically do not make any a priori knowledge. Am I working with a cloud optimized HDF5 file or not cloud optimized file? But again, it's slowly coming to that. And the next release, which I don't know, some months from now, we'll have a bunch of these new improvements. I like to single out this zlib-ng
1 minute.
support because that's a faster zlib implementation for compression. So if you're really you like the zlib compression method, this should be at least give you some faster performance, unless you want to change the compression method altogether. And that's that. Thank you. All right, now it's Iron. Yeah.
Great, thank you, Alexander. So now it's Sean's up.
All good.
Yeah, thank you. Sean, which one are you?
I'm ESIT Virtual Czar. It's Virtual Czar.
Thank you.
So I think Alexander did a great job of teeing this up. So this is a good follow up. Just as a show of hands, how many people are using Kerchunk right now? Just for context. Not enough. Not enough. Hi everyone. I'm Sean Harkins. I'm from Development Seed, and I'm going to present some work that is definitely not mine at all. I'm going to just call out Tom Nicholas here. He's been really the one spearheading a lot of this work. And this is a version of a presentation that he gave for the Pangeo showcase. So I'd suggest if everybody gets a chance, they go check him out and watch the video of that. He's British. He sounds much more sophisticated than I do talking about these things. So yeah, if you get a chance. And again, a lot of people are working on this project right now. So I just want to call out all the contributors as well. And actually, just to go back, for names, we have a lot of confusion all the time. People asking me whether we say virtualizer or virtualized czar. It's like the pirate, virtualized czar, just if there's ever any confusion. So what are we going to talk about today? I'm going to talk about cloud-friendly access to archival data, czar virtualization, this new package that we've been working on, virtualized czar, and some of the plans we have for pushing some of this work upstream directly into the czar API. So a lot of people have already talked about this problem today. What can we do to provide better cloud optimized access to these legacy formats? I don't want to say legacy. Somebody took offense to the term legacy, so I'm going to try and say archival. That's a little bit better. But we have so many archival files, huge volumes of NetCDF files, HDF files, and GRIB files, and we want them efficiently accessible on the cloud. Czar, as a few people have mentioned, is a much better approach for the cloud because it makes a clear separation between data and metadata. It gives us inherent scalable I/O, and it natively supports these cloud-optimized access patterns. But providers like NASA and NOAA, they don't want to change the data processing pipelines that they have to write different formats, and they're a little hesitant to make changes to something that's been working well for them for a long time. So how can we solve that? Czar virtualization. The library Kerchunk, created by Martin Durant, he was the one that really pioneered this idea of a virtual czar-like layer over a top of a large set of NetCDF files that contains pointers to their byte ranges so that we can have what appears to the user like a single consolidated czar API, but underneath is actually just a big grouping of NetCDF or GRIB or GeoTIFF files. And this is really powerful because it can just point to the data in a different location. And it also gives us the idea of like an index of all these files. So instead of trying to create a separate metadata solution, we have all this index information stored directly in this czar-like API. So what are some of the advantages of this? No data duplication. So we're only duplicating references and metadata, and the original files remain in their same location in an unchanged state. And if people follow some of the chunking recommendations that Alexander provided before, our access patterns can be as performant, if not more performant than ZAR in some cases, depending on the fact that the files are well structured underneath. What are some of the disadvantages? Again, if somebody makes a poor decision, NASA and NOAA, about the chunking structure that they've used to produce their files, we can't go back and change that. So Rich showed some of the rechunking operations that he's done, but when we make virtual layers on top of that, we're stuck with what we got. And we also can't really guarantee the consistency if a file changes. So what's Kerchunk do right now? It makes a ZAR-like layer, and we do that by using some internal methods in Kerchunk. We find these byte ranges and offsets using single HDF to ZAR. They get represented as a nested in-memory dictionary. Kerchunk has a special function called multi-ZAR to ZAR, and it writes them out in a Kerchunk reference format, usually in JSON or Parquet. And so we get this entry point that behaves like a ZAR store. So Kerchunk's been great, and I think it's really was like revolutionary in the concept that it had, but it has some issues and some problems that were kind of inherent in its design. Right now, concatenating multiple stores together or multiple files is complicated. There's some abstractions that are in the code base that make some things hard to express. And this multi-ZAR to ZAR function is really kind of bespoke, and it's really difficult to reason about what's happening inside of it. As well, like this in-memory dictionary representation that we use for the offsets and the manifest information is really large in memory and difficult to manage. And most importantly, the output files that we create are not real ZAR stores. So the only way that you can access them right now is using Python and FSPEC. So that leaves all of the other players that are using other languages on the sidelines. So for Tom, he was really like in the weeds, us at Development Seed as well, making really large Kerchunk indexes for big data sets. And we were feeling all these pain points. We filed a few issues, we had some discussions, and we really just wanted to come up with a new way or a better, more efficient approach to do this. So what we want from all this is we want to make concatenation of all these different files as easy as using Xarray concat. So Xarray has extremely good array concatenation logic, and we just wanted to be able to take advantage of that directly. We wanted a better in-memory representation of all these chunk manifests that was efficient for billions and billions of records. And we wanted a real output ZAR store that any ZAR implementation could use. So how do we start on this? The first step is this chunk manifest concept. So ZAR as a specification is really simple. It's really just some metadata about chunks and a map to where all of those compressed chunks and bytes live. Kerchunk really opened the door and showed us that we don't have to keep those chunks and all those files in the same ZAR store. They can live anywhere. So what we can make is just a really nice representation that's a list of paths to where the files are and the byte ranges that each of those chunks have. And so again, if we're looking at 3 time steps of a certain data set here, our chunk manifest is really simple. It's just a location where the file is and the offset and size information for each of those chunks. So what is this virtual ZAR package that we're working on? What we really want is to be able to combine all these reference files that we create in memory using Xarray concatenation methodologies. So we already have this Xarray API for concatenation. So all we did was make an array type internally that Xarray can wrap. So when you use Xarray now, if you ever look at it carefully, the underlying array type that it uses is NumPy generally, or a Dask array. But we can make another manifest array, which wraps up these little chunk manifest objects. And then we can do anything that a regular Xarray object can use within limits. And so this is great. We have this virtual ZAR package working quite well right now, and I'd encourage everybody to go and check it out. There's still some rough edges and some things that we're working on, but that's really just manipulating references in memory. So the way that it works right now, you can't really do anything with that unless you write out the results of it into a Kerchunk file that you can use. But the real goal for us is to try and push all of this work up behind the ZAR API. So there's a new chunk manifest ZAR enhancement proposal that would allow us to basically store all of this chunk manifest information inside the ZAR store And then when people access the Zara store, we're just delegating the requests for the underlying bytes out to the files where they live. So everything would go through a Zara interface, and everybody would just talk to a Zara client, but you know, they're only talking to the underlying files on the side. So yeah, like it's really easy to do that as well. The specification we have right now is to just stuff this manifest JSON kind of at the array level, so that there's a pointer. We're exploring some more efficient storage mechanisms for that, but we still haven't settled on what the final implementation will look like. Most importantly, like I said before, this means that any like valid Zara client should be able to work with these things. So if somebody is working with a Rust Zara client, or more importantly, a JavaScript Zara client, they can read bytes directly from netcdf files. Yeah, so there's still some open questions on this virtual concatenation ZEP as well. This is another issue we have. Like when we look at a single Zara array, we kind of assume that they are all using the same, the array itself is just using the same codecs. So we can't merge files with different encoding or different compression. But there's some open ZEPs right now with this virtual array internally that might allow us to work around that. We don't really know what that's going to look like yet, but the hope is that we would actually be able to make internal representations of different codecs and then expose them as a single uniform codec on the outside.
1 minute.
Yeah, 1 minute. Yeah, so we need a more general version of concatenation that also needs to be serializable to a Zara store. So yeah, again, virtual Zara stores over legacy data are a great idea. This virtual Zara package, again, it's an alternative to what Kerchunk has now. We're still in the early stages, so I would encourage people to come and try it out and give us feedback and let us know where we can improve things. It uses Xarray, so it's really intuitive. And again, we have a lot of ongoing roadmap work to push all this work upstream behind the Zara API. And yeah, I'd encourage everybody again to go check out Tom's presentation because he can explain this a lot better than I can. Thanks.
Yeah, so while our final speaker, James, is making his way up to the front of the room, I'm going to ask that all speakers who wish to host a breakout group in the second working session could come up to the room at the end and just, you know, sort of share with the attendees exactly what their breakout topic will be, whether it's just a continuation of a discussion of their presentation, or if it's something else. Yeah, so please stick around for that at the end. And thanks, James. Go ahead.
Oh, thanks, Amy. Yep, so my name is James Gallagher, and I'm just the presenter. I'm not the author. Ayush Nag is the author of this work, and this is another Virtually Zara, I hope I said that right, presentation. So, so here's the problem that he was looking at. He was a summer intern at Physical Oceanography DAC, and he was looking at accessing SWOT data, and he wanted to look at 21 days worth of it. That's about 620 files. And so he said, you know, the problem is that reading and concatenating all these files is a problem. It's really inefficient. And in fact, it's so inefficient that exploration, analysis, and visualization are all essentially impossible. So he began looking at Zara as a way to make that work doable. So he compared those two technologies, and you get the graph on the right, which you've now seen for like, what, the 8th time? And so I probably don't need to explain too much that Zara is a way of optimizing these sorts of things for when you're working with the data in the cloud. But the thing is that he didn't have the capacity to reformat all of these data files in Zara. Obviously, actually, he did have the capacity to reformat some of them because he got those timing data. But in general, he didn't have the capacity to reformat all of them. And he wanted to look at a more general solution. He was working with the Virtually Zara folks. And so he said, okay, one of the things you could do is you could use Kerchunk to build these sidecar JSON files. And those JSON files, as we just heard, they store the meta information about where the data actually reside in the various files. And then they treat those files as essentially a big bag of bytes when they go in and they pull different sections out. And you could compare that with Zara, which shards the files and, as Patrick said, leaves the problems to somebody else. But essentially, they result in equivalent access times. You can debate, it's like 10% plus or minus, but essentially equivalent. So if we look at that as a solution visualized, you have ZAR on top, and you have ZAR plus some metadata, and you can feed that into Xarray. And you can get these accesses. Or similarly, you can take NetCDF and the ZAR metadata standard that comes from the Kerchunk JSON files, and you can feed that into Xarray as well. So the thing is that building, as we also heard, building these sidecar files takes time and effort, and there's lots and lots of granules. So Ayush knew that OpenDAP and NASA have been working on building another kind of sidecar file we call the DMR++, which is a slightly less upscale name than Kerchunk, but whatever. But anyways, and this actually was originally designed to be a way to cloud enable OpenDAP servers, so that when these data files were moved to the cloud, NASA could continue providing OpenDAP access, the same kind of OpenDAP access that they provide their on-site servers. They could provide that with their cloud-based servers as well. So it turns out that the semantic content, I'm calling it semantic content, of a Kerchunk file and a DMR++ file are effectively the same. Now, we can argue over the differences a bit, or maybe not argue over them, but drink over them at least. But they're pretty trivial. And so suppose that instead of Kerchunk, we wanted to use the information in the DMR++ files. The advantage being that the DMR++ files in many cases already exist, and they're sitting right next to those files in the cloud. And there's an ongoing commitment to make more of them as time goes on. So this solution, and I've deviated entirely from my plan to talk at this point, so I have no idea if I can finish on time, is that these things are going to work with the existing NetCDF HDF5 files. They'll also actually work with existing HDF4 and HDF4 EOS2 files in the future. And then we're going to use Earth Access and virtually ZAR. We're going to parse the DMR++ and build this equivalent ZAR metadata object that gets fed into Xarray, which can then read and subset these things. So visually, it looks like this. It's really architecturally the same as what we saw before. We're just moving a few different things around, but actually not much very different. CMR goes out, finds the stuff, and then the granular information that comes from the DMR++ goes into Earth Access, which pipes it down to a virtually ZAR module, which then parses that and returns it as the ZAR metadata. Goes into Xarray. Xarray has no idea that it's working with this really weird XML format. So the solution has been implemented by Ayush, and again, query load and analyze is accomplished by Earth Access. Thank you, OpenScapes. And that uses CMR. It handles the parallel read of the DMR++ files, or parallel read and parse of the DMR++ files. And it's a working proof in concept at the time that he wrote this presentation, which was a few months ago. The final API is still in works, but you can see some example uses in a Jupyter notebook and so on. The benefits. Well, so part of the benefit, possibly the biggest benefit not listed up here, is that the DMR++, this is actually a repurpose of something that was originally designed for a different use, but we intend to produce large numbers of these documents. And we also have in works the plans to produce these on the fly. This also seamlessly integrates a data query engine with searching. And this is a kind of a movement from the notion of searching as a step that happens before access to taking the data, the logical data model of a multi-granule entity, and thinking of it as producing an aggregation and then accessing over a time range using the dimension subset capabilities of the data models as opposed to a separate searching step. And so he also points out that the DMR++ parser in Python is extremely fast with only several milliseconds of overhead. Future steps. So he's asked for streamlined access to the DMR++, and that's actually in our work plan to produce a simpler way to access these documents directly, and similarly a way to produce these documents on the fly. Also, for very large DMR++s, very large is a relative term, of course, but we would like to break them up into pieces, because oftentimes across a single collection, there is repeated information that occurs over and over and over again. So we could store that once, read it once, but use it many times. And then finally, the virtually czar work is headed towards the czar specification, as we heard in the previous talk. And in fact, few people get luckier with the previous talk than I did, because Sean knows a whole lot more about virtually czar than I do. So, with that, I'm done. We can head out, or I can answer questions, but we could just head to the next session, actually.
Hey, yeah, so I was hoping that all of the speakers that wish to host breakout groups could make their way to the front of the room. And while they're doing that, I just wanted to repeat that as a virtual option, or even if you want to participate in person, there is a cloud optimized data product development guide. The URL for that, I'm going to put in the cloud computing. It's in the cloud computing Slack channel of the ESIP Slack. I will also paste it in the chat here, but I know not all of you can see that. So if you have access to, so there's a 10 URL, tinyurl.com COPD -guide. And I've also added a link to that in the notes document for the next session. So if you know how to navigate the Google Drive, you can get to it there. But the easiest thing is probably to join the ESIP Slack channel if you're not there already, or grab it from somebody else. So with that, yeah, thanks to all of our speakers, especially for staying on time, because now we have enough time for everybody to sort of give a short pitch for what they'd like to continue talking about in the next session. So let's just go, James, maybe I only see you, so could you just sort of, maybe you can start.
I'm the only one.
You can start and pass it off to other speakers in the room if they're not at the front of the room.
Sure. Well, I'd like to actually talk about reorganizing HDF5 files, possibly in the NASA Cumulus workflow, so that it would be easier to build DMR++ things on the fly. And I'm also really interested in coming up with a way to, on the fly, transform DMR++ into Kerchunk JSON as well. And as part of that, thinking about the about codifying the evaluation semantics of both the DMR++ and Kerchunk objects.
Yeah, so I can definitely, whatever people feel like, either approach me with questions about cloud optimizing HDF5 files, or various ways how you can connect the library and the Python world of accessing and things like that, or we can try to write something on this guide. I'm open for whatever people feel like it's more valuable to them. I'm here to help.
Yeah. Similarly, if anybody's interested in like rechunking, like how the details of like how we did the rechunking, like on a parallel, on HPC, like job array and stuff like that, or anything about chunking in general, or anything about like maybe on the client side, how to more effectively access these collections, I'll be around too. So.
Yeah, we have a PR that's going to land soon in Virtualizar that will replace the current kind of Kerchunk offset generator or chunk manifest generator logic that we use. I'd actually talked to Alexander yesterday because it's like invaluable to have somebody with the deepest expertise on HDF in the world right there to help us like verify that that's good. But we also really want users with bizarre data sets or difficult data sets so that we can test these things and make sure that we're catching all of the HDF edge cases. So if people have done Kerchunk work before and had difficulties generating references for their data sets, or if they just want to see how their data sets work, they can come and sit down with us. That would be great.
Nice, thank you.
Happy to talk about really whatever if you want to geek out about file formats. I'm here, but also optimizing things that aren't like nicely gridded files like swath data. That would be a fun one.
I just wanted to add too that after Sean's talk, Martin Durant is very much in favor of virtualized R. It's not like, he created Kerchunk, but he's like 100% behind the.
Yeah, I should have said when I said alternative, like I just to again say Martin really came up with this concept and everything, and he pioneered this concept. But I think he recognizes too, like we can modernize that and we can do something that's a better user experience for people. So we're really just trying to transform what he's done into something that's a more seamless user experience.
I'll take like 4 minutes of questions, I guess.
Where's the mic?
Oh yeah.
Oh, it's there. Yeah, I was here.
Yeah, just repeat the question. Let's just repeat it.
Oh, just repeat it?
Yeah.
Okay.
Yeah, it's just a question. Have someone thought about standardizing DMR plus, ZAR, and HDF5 description like HSDS and generate HDF map? Because it's the same information stored in different JSON or XML. It doesn't make sense for every group to write to different formats. Then format extent of coming with a standard and doing this thing once. So.
Yeah, I can talk a little bit about that.
Repeat the question.
Oh, sorry.
Did you hear that, Amy? Did you hear
No,
that?
Yeah, repeat it.
Yeah, I think the question was just on why we don't have standardization for this chunk manifest representation or chunk map representation. So I think there's a few things happening. I'll let James talk more about it because he has the longest experience. I mean, DMR++ has been around for how long?
7 years.
Yeah, so that's one thing is that that predates the work that we were doing a lot. For us on the ZAR side and the virtualized ZAR side, we're really focused on the best in-memory, the most efficient in-memory representation for these things. So we want to make sure that in memory we can use the smallest footprint for these things and the most efficient access patterns for them. But then also from a serialization perspective. So on the ZAR side, when we're trying to decide how we're going to serialize these chunk manifests inside of the ZAR API, we're looking at array representations, we're looking at direct arrow representations. We really just need whatever is going to be the fastest, most computationally and memory efficient way to do it. And the representations we have now are too verbose for that. So we need to change what we're doing for sure.
I can maybe say, first of all, we want all to work more. So there is no incentive to standardize. I'm just kidding. I'm just kidding. But the other thing is that both DMR++ and the Kerchunk, they already have to plug into already existing formats. So the story would be why the property, the structures in HDF5, the internal structures of HDF5 file format, why are they not standardized to something else? They all sort of are internal to HDF5 way of doing things. It's a similar philosophy. DMR++ has to speak to the Hierarchs way of doing things, and Kerchunk has to speak to the ZAR way of doing things. So it's that's why they sort of the same purpose but different way of doing it.
I guess so. I don't particularly disagree with that, but from my perspective, the problem that we've been facing with DMR++ for the past years has been that conceptually the ideas are extremely uniform. Like I said, semantically, Kerchunks, JSON, and DMR++ are the same thing conceptually, but in practice they're not, and that is because we've had to drill down into the kinds of nooks and crannies within the HDF5 data model, the computer science data model, not the science data model, but the bits and bytes. We've had to drill down into the nooks and crannies of that. Like there are 12 different ways to represent strings in these files, 12 of them, okay? There are 3 different types of gross data organization, and so on and so forth. There are multiply applied filters, some of which include applying algorithms like deflate more than once on a chunk. All of this has to be captured in order to restructure these things. And as NASA has pushed us to provide support for more and more collections, we have had to go beyond the conceptually simple and straightforward to the fairly obscure, or what a friend has qualified as quirky data. And so I think this drives a lot of the differences, because I think the Kerchunk philosophy is to look at an optimized memory representation. And the DMR++ philosophy is to try to support as many existing archival instances as possible, not HDF5, but instances. And that's why we've also gone on to HDF4 and HDF-EOS2, which is shockingly more complex than HDF5. I'll tell you that right now. So this is why I talked about the notion of coming up with ways to notate in a formal way the semantics associated with the interpretations of these documents, because that's really a key thing. And this is a thing that we can pass forward, because we're not just providing access to these archival formats, but we're really documenting their internal semantics in something other than the C code that implements their APIs. And this is really crucial because these data are important over time, right? You know, today's format is tomorrow's legacy, right? That's true, right?
All right. Thanks, James.
I think
Yeah.
just one point on James's as well. Like we also can't
Microphone.
Oh, yeah, sorry.
Online.
We can't standardize the data model to a NetCDF or HDF5 based model for virtualize R, either, because we are trying to support a bunch of formats. So we also are supporting message based formats like RIB2. Anything that we can read in offset, basically. Like if we can take part of the file as an offset and it can be represented as an array, we're going to do it. So so there's a big kind of semantic mismatch for those as well.
All right, we're at break. Thanks, everybody.